done is to use the Sony Aibo robotic dog as sort of a symbol of where we're going in the course. And I just thought you might want to briefly see him. He doesn't get much action these days. And if you've been on my Instagram channel, you know that this is Einstein and we're celebrating all sorts of things with Einstein. But you might feel cheated if you never ever saw him in the course. Yeah, and the exciting thing behind me is combining Chat GPT and DALL-E to make new drugs. And it's a very exciting prospect in general, but it also probably would allow us to make new immunosuppressive drugs, particularly useful in xenotransplantation. Yeah, so it's directly relevant to pig to human transplants and things like that.
Could you send me that article or the link to the article?
Sure. I would be happy to. And now there we go. Yeah, so you can start sharing.
Speaking of that article, actually that is very interesting, and that's why I said, could you send it to me? Because I learned that some people have already started selling books on online places. I will not name them, but the books were made with stories. Stories are written by ChatGPT and illustrated by DALL-E. So yes. The author didn't do anything. They just put the stuff together, and they're selling it already online.
Yeah. But whatever spirit you get from a human author, it would probably lack some of that. It wouldn't be quite as satisfying.
But people buy it just because they're curious.
Sure. Yeah.
And whoever had that idea will make money, even though they didn't do anything.
Yeah.
So let's see. I'm sharing now. I will start. So go on.
Yeah.
You see my slide?
Absolutely. Yeah.
Good. So this is the third part that I called down to earth machine learning. So we'll talk about machine learning. And remember, in the first two parts, I talked about AI, and I mentioned that AI is a subfield within computing science, and part of AI is machine learning, and I'll talk about machine learning today. And one particular paradigm in machine learning, in supervised learning, is deep learning. Okay, so what I wanted you to remember is that deep learning is machine learning, and machine learning is within AI. They're not synonymous. Also in the previous lectures, I talked about why the resurgence of AI now, since AI has been around for like 70 years. And basically it has to do with the available data that we have now. It's massive. The fact that our computers have evolved, and they're incredibly powerful. And also we have a new algorithms that we can run on this data using those big machines. I also mentioned about precision health, precision medicine, and how machine learning can play a significant role there. I gave you many examples. And I also talked about some incredible achievements in computing science, and particularly in AI, artificial intelligence, from Deep Blue crushing Garry Kasparov in '97 to recently we are talking about ChatGPT and DALL-E, these huge systems that only very few can afford building them. The example of ChatGPT was open to the public. Something that you may not know, ChatGPT, to run it, just to run it, when you have millions of people accessing it and testing it per day, it requires $3 million. just between heating and processing power and things like that. And that's one of the reasons why now they started a version of ChatGPT where you pay basically. You have a subscription to it. So these achievements actually have led to these hypes, ups and downs each time. Oh, AI now is taking over, and then we forget about it. Oh, AI is taking over again, and forget about it. And then recently, with ChatGPT, everybody is talking about AI. So what is ChatGPT? Basically, ChatGPT is just a large language model, and there are many of them. Okay, and what is it? It's basically calculating the probability distributions for different words in a given language, and it learns it from a massive, really big collection of text. And then when it learns, you can use it to predict word sequences. And that's how it generates sentences, sentence after sentence, and it can generate paragraphs and long documents based on this massive training data. So the modern large language models, they use an architecture called transformers. This was introduced a few years ago by Google, and transformers basically add some kind of parallel processing in calculating these associations between words, and it allows you to put some attention on some words more than others. And this is how they build these language models, and we get incredible results. I'll give you some examples where actually it's hilarious. You saw fascinating examples for sure, but here are some examples where it fails miserably. The thing is that these language models don't make any reasoning. Not only that, they don't know anything about the world except these associations between words that it learns from these texts. So here we ask it, what is the world record for crossing the English Channel entirely on foot? And it gives you an answer. And you think, some people have said, oh, that's it. Now search engines will disappear. We will have ChatGPT will answer all these questions. No. Be careful, because ChatGPT and the like, they create facts. This is what we call hallucination. They hallucinate because they answer a question based on these probabilities, this word after this word, and then they can create something that may look very true. The thing is that you can ask it, okay, give me another answer to the same question. Answer it different. So you saw this answer here, like 12 hours and 10 minutes, and give me names and stuff like that. If I ask it again the same question, it'll give me another answer with a different time. Now, in between, somebody else beat the record. So you have to be very careful about those facts, because not only it hallucinates, but it answers with confidence. So when you read it, you think, oh my gosh, that must be true. Okay. And there is no way to ask it, where did you get these facts? So we have now new language models that are able to explain what they say from where are the resources where they got this information from. Here are some interesting examples again, where you can see that because they trained it also, they actually trained it not only to calculate these probabilities, but also they use some kind of reinforcement learning with humans to know what kind of answer is good and what is not bad, what is not good. And they try to remove some of the biases and make it polite how it answers and things like that. Here we ask it, what gender will the first female president of the United States be? And it's trying to be politically correct to the point that it's ridiculous. I'll let you read it there. So recently, actually, what day are we today? We are the 7th? Yeah, we are the 7th. So 2 days ago, Yann Lequin, he's the chief AI scientist at Meta, so Facebook, he tweeted the following. He said, before we reach human level AI, we will have to reach cat level or dog level AI. We are nowhere near that. We are still missing something big. So large language models, linguistic abilities notwithstanding, so because it's amazing what you can see. I mean, the output is incredible. A house cat has way more common sense and understanding of the world than any language model. So there's no understanding of the world we live in. And it doesn't make any reasoning on that world to be able to answer these questions. Okay, so, and this is not anybody who's saying it. I mean, Yann LeCun saying this means a lot. Yann LeCun was the Turing Award winner in 2018. Turing Award is like the Nobel Prize for in computing science. He's one of the pioneers in deep learning. He was a postdoc with Jeff Hinton at the University of Toronto. He's the one who in the 80s created the system that recognizes hand-written digits to read checks and postal codes on envelopes. So he's quite famous. We also talked about the singularity very quickly, and I mentioned the different ways to reach that. And the one that I truly believe in is number 3, where we will mix humans and machines to provide the humans with abilities that we didn't have before, and probably also some capabilities with the brain. So either memorizing more or being faster, or thinking faster, or something in parallel thinking with me and giving me that information to make that reasoning or whatever. So why computational intelligence, which is another term for artificial intelligence, is important? It's because not only we will be able to build these tools, as I mentioned, but also it's allowing us to understand our own intelligence and how the brain functions. We still don't know how the brain functions. We have many hypotheses. But the more we try to build these systems that are as intelligent as us, the more we actually have opportunities to understand how we, the human machine functions. I also mentioned the Turing test. So Alan Turing in the 50s wrote a book, Computing Machinery and Intelligence. And in that book, he was trying to say, what will we do with these machines that we were using during the Second World War to decode and all that stuff? Now that we don't have a war anymore, what will we use them for? And he tried to imagine in the future how it will be and how intelligent they will be. And he tried to come up with a test that will allow us to say this machine now reached the human intelligence. Okay, so with ChatGPT, nobody believes in Turing test anymore, because actually ChatGPT can generate things that many humans can't, certainly not in a few seconds. So obviously this Turing test, which I remind you, it's a test where a human is conversing with some entity behind the curtain, and you don't know if that entity is a machine or a computer. So if the human judge on one side cannot distinguish whether it is a machine or a human, then if it is a machine, then is actually as intelligent as a human. So people have started thinking about alternatives to the Turing test. The Turing test is meant to judge how successful an AI or machine is able to simulate human intelligence. Doesn't really mean that it's actually intelligent, but it simulates this intelligence through a kind of a chat conversation. And many people have demonstrated, even before ChatGPT, that we can build a chatbot that can fool human judges to make them think that this chatbot is actually human. And I told you about this Eugene that was pretending to be a Ukrainian teenager, 13-year-old, and was able actually to win the prize for $100,000 because I think 1/3 of the judges were fooled. So people decided to come up with other tests, and here are some alternatives I just mentioned very quickly. So there's a test called the Vinograd Schema Challenge. This was suggested by a professor at the University of Toronto, Hector Levesque, and he basically said that instead of having this conversation, I will ask specific questions and see if the computer is able, or the machine, the AI is able to make reasoning and answer. For example, the trophy would not fit in the brown suitcase because it was too big. And then the question, what was too big? Okay, so too big, obviously, it's not the suitcase, it is the trophy. And I can reverse it for small or, and so the test is a set of these questions that require reasoning in order to get the right answer. And currently, the chatbots are not able to do that. The other test is called the Marcus test. It's suggested by a professor from NYU, New York. It's a kind of a video comprehension question. So the idea is to watch a TV series or watch a YouTube video, and then we get a set of questions to see whether the person or the machine that watched the video is able to understand the content of the video and summarize it to some extent. So why did so-and-so do this and that? Okay. So he said, this is a quote from him in an interview, he said, no current AI can currently come close to doing what any bright, real teenager can do, even a child. Watch an episode of The Simpsons and tell us when to laugh. The computer cannot. So the other test is the Lovelace test. This is from named after Ada Lovelace, the first known programmer. So this was suggested in 2001 by a professor at RPI in New York. And basically, it looks at the creativity of the machine. And the test is to describe some kind of task to create something based on the style of somebody. And if the human referee can judge it, like in a class in design, for example, the professor asks the students to design something, and there's a criteria to evaluate them, then a human would be able to say, whoops, it reaches the human level or not. I think this is actually, with DALL-E, this is already surpassed, in my view. The other test is called the construction challenge, or some people call it the IKEA challenge. And the idea is to, if, for example, the drawing or the explanation in text, in speech, of a piece of furniture, and you say, build it. Okay? And you have to think about the different stages and describe what you're doing. Apparently, it's only intelligent people who could do that. And then another test is the visual Turing test. So the argument here, this is suggested by a professor in the UK at the University of Exeter. The idea is to not just focus on language, like Turing test is based on language, but also on perception of the world we live in. And the test is giving you a scene and a picture, and then I ask questions about the scene. Like, for example, here I have a table, I have things on top of the table, and I'll ask you, look at the scene and answer the question, where is the coffee cup? And I have to describe where it is or answer with multiple choice questions. And then finally, there is what we call the reverse Turing test. So the reverse Turing test is, instead of me, the human judge, deciding whether behind the curtain that's a human or a machine. It's actually the machine that is trying to identify that I'm a human or not. Okay, and just explaining why it thinks that I'm a human or not a human, because you need some intelligence to be able to do that evaluation. But now, well, there are some tests like that exist already, like the CAPTCHA, or click on the whatever tiles in the image to tell me where are the light, the lights or the signs or whatever. Those tests, CAPTCHAs, are not really intelligent whatsoever, but it's in the same kind of spirit. It's an AI on the other side trying to determine whether I'm a robot or a human. Okay. Any questions so far? No? Let's see let's have some fun and look at some examples of another system called DALI. And probably most of you have heard of DALI. DALI is also from OpenAI, and it basically takes a description and generates an image out of that description. This is an example where I asked, it's not me, actually, all the people, I just got it from online. Somebody asked, give me a photo of an astronaut riding a horse. It is funny. It's actually quite interesting. It worked very nicely, but at the same time, you realize that it cannot be realistic. If somebody asked me to draw an astronaut riding a horse, I will have somebody wearing like an astronaut, but riding a horse on Earth, not in space, because I know this cannot be possible. There's another interesting one here. A raccoon playing tennis at Wimbledon in the 90s. I don't know why that is in the 90s, but it's actually quite impressive. You can even ask it to take the style of somebody. Here's the question: is a Raphael painting of Madonna and a child eating pizza. You can see the pizza here. And then the style is actually quite impressive how it was able to do that. Here's another imaginary picture: an Italian town made of pasta, tomatoes, basil, and parmesan. I mean, I wouldn't be able to do that. But the more you can ask it the same question again, and it has some creation. It creates more things. Here's the same question asked 3 times, and you get 3 different answers. Olive oil and vinegar dazzled on a plate in the shape of a solar system. And the danger here, well, I'm not talking about the danger for the artists and all that stuff, but the danger is that it actually can create things that are believable, that are realistic. Here's the question: Spider-Man from ancient Rome, and it generates a realistic picture, and people may believe, oh my gosh, this is from the Roman ruins, and it's Spider-Man existed already. You ask it again, it can generate another picture. Here's another Spider-Man, like in Pompeii, one of those people that was surprised by the volcano and died. And here's another realistic one. It's a funny one. I really like an ancient Egyptian painting depicting an argument over whose turn is it to take out the trash. And you even can see some of the damage on the wall, and you may think, gee, this is real, but it's very fake. Okay, let's talk about now the down to earth, the machine learning thing. So remember, this is the picture that I gave you last time, and I mentioned that in computing science you have AI as a subfield, like many other subfields, and within AI you have many specialties, but one of them is called machine learning. And in machine learning, I have supervised, unsupervised, reinforcement learning, and so forth. And within the supervised learning, I have deep learning. So I'm going to zoom in here, and I'll tell you a little bit more about machine learning. Okay, so how do machines learn? How do they learn to draw things or predict words or do other things like the examples that I gave you for precision health. So the metaphor that I often use is the following. I have a set of buckets, colored, gray, red, blue, green, and so forth, and I can number them 1, 2, 3, 4, 5 to n. I have n different buckets, okay? And then I have a pile of balls, and these balls have different sizes, different colors. They have different textures, different weights, whatever. They have different characteristics, and I have a pile of them. And then I'll ask a child, and the child will represent the computer. And I'll tell the child, hey, look, sit next to me and watch me what I'm doing. And you should learn what I'm doing. And I grab a ball and I look at it, I touch it, and then I put it in a bucket. Grab another ball, look at it, touch it, and then put it in another bucket. The task is to learn, how do I put the balls in which bucket? So how do I decide which bucket I should put the ball in? Okay. After a while, the child will start asking questions. Is it the weight? Is it the texture? Is it the size? Is it this color? What makes me, or a combination of these things, what makes me decide to put them in one bucket or the other? Okay. This is what we call classification. I am classifying these balls in different buckets. And after a while, observing me, the child will say, I don't think it's the weight. I don't think it's this characteristic or that characteristic. Must be the color. And if I give the ball now, this green ball to the child and say, okay, now it's your turn. You predicted which bucket I would have put it in. Then it'll choose the green bucket if it believes the color is what determines in which bucket to put it in. Okay. So basically classification or machine learning prediction is building this predictive model that tells me how to associate the features from the object that I want to classify with these different classes. Okay. So what I have training data. This is exactly what I was doing by showing to the child what I'm doing with the balls, put them in the different buckets. I'm labeling them. Okay. So I have data that is labeled by an expert, and then the computer, like the child, will observe all these training data and then build a predictive model. Okay. That predictive model, let's put a face on it, and now I will use that predictive model when I'm provided with new data that hasn't been labeled. Okay. And I will use that model to predict the labels automatically. That's exactly what happens, for example, with email. When you get email, some of it is good, and you will save it, you will reply to it, and so forth. You will reread it, or who knows what. Well, some of the email, you'll dump it. It's useless. It's spam. So the program is observing your behavior, how you handle emails, and will compare the features of the emails, where it's coming from, what time it came, or what are the words used, and so forth, whatever the characteristics that we'll use. And it will build a classification model, so predictive model, that will associate the features from the email to the class, whether it's spam or non-spam. So I have now new email coming, and that model will be used to automatically label my email. And the same thing happens when I have images. So here I have mammograms. The radiologist will label them. This is cancer, this is no cancer. And then I will learn from that and associate features from the image with the class label. And then when I have new images, I will use that model that I learned to automatically label these. Now, it's not all rosy like this. There are many challenges. The challenges, for example, what are the features that are relevant to determine one class or the other? Another challenge is How do I optimize the algorithm so I can efficiently and effectively do the separation between the classes? Another one is, how do I represent the knowledge that I learned in this cloud? So how do I represent it such that I can exploit it later here effectively? Okay. So there are still many questions, but people have managed to do amazing things already with the techniques that we have. But it's not a solved problem. It's still an open research question that people are still working on. There's some, I think I don't know if I talked about some of the examples of machine learning that are used today. Like you probably heard of the autonomous vehicle. Autonomous vehicle has to, at any given time, make many decisions that we take for granted. For example, recognizing the signs, that's a classification. Is it a stop sign? Is it a no left turn? Is it a no parking? Is it a speed limit or whatever? Also, when you have things in front of you, is that a pedestrian crossing, or is it another car, or is it a plastic bag flying in the, because it's windy, or who knows? These things are also classifications that are happening all the time. And so within the autonomous vehicle, there are many, many different classifiers. They're all using machine learning. So we train them on large collection of images of pedestrians and signs and so forth. Handwriting recognition. Remember when I talked about Zaiane, he's the one who actually created the system in the 80s, but now we can actually even recognize handwritings and so handwriting for letters and for formulae as well in math. And it's very, very, very effective. This is also based on machine learning. We train the system to recognize different symbols and different ways of writing it and so forth. Spam filter, I mentioned. Credit fraud detection. So when you swipe your card and the machine is sending the request for the transaction, do you authorize this, yes or no? Well, there is a machine learning algorithm that checks whether this is a legitimate transaction. Does this purchase match your behavior, your past behavior of transactions? And so it learns from all the transactions that you did in the past, and it knows what is valid, what is not valid, and can give you this answer when we ask for the authorization. This is used every day for millions of transactions every day. Financial applications, particularly for high-frequency trading, for example, to detect what is fraudulent, what is not fraudulent, what is legit, what is not legit. Recommender, financial credit. Oh, yes, this is the example for people going to the bank asking for a loan. Should I give a loan to this person or not? Based on the characteristics of that person, I already built a classifier that learned who is who I can trust, who will pay me back my loan, and who will not. And when I have a new customer, I can predict that based on what I learned from past experience. I means the program in the bank. So recommender systems. Recommender system is when I'm trying to recommend a product or service to somebody. I want to maximize the fact that they will actually be happy with it, they will buy it, or they will come back and so forth. I will learn to predict the rating that they will give based on the ratings that I observed from other customers like this person on other products and so forth. So they use machine learning. Adaptive interfaces. I'll take the example of Facebook. All of you are familiar with Facebook. You may have 500 users, 500 friends, or some people have way more, like 1,000 friends. When you connect to the system, you're not going to see all the activities of everybody out of the 1,000 people, because you'll be overwhelmed with all the activities that they did. So in the news feed that you will get, it'll be selected by the program, the algorithm we call it. It'll be selected by the algorithm based on what it predicts you will likely interact with, you will probably like or share or comment on, and that is learned automatically based on your past activity on the system. So it uses machine learning to do that. I'm skipping these other ones because we don't have time. And of course, I talked about medical applications last time, but I'll just remind you again here how machine learning is used. This is the example of a patient, and I'm trying to, it's a new patient, and I want to predict whether the disease that she has right now will reoccur after I treat it or not. I have some characteristics of this patient, and I need to predict this, but I already have historical data from other patients, and I know for which patient it reoccurred or not. So this becomes the buckets. I have two buckets, yes or no. And I build a classifier, predictive model, and I use that predictive model to predict now for this new patient whether it will reoccur or not. There are other issues as well. Like here, I said yes, no. In classification, it's not always that you have two buckets, yes, no, cancer, no cancer, spam, no spam. There are many problems where you have multi-classes. So this is the difference between a binary classification and multi-class classification. The difference is that in a binary classifier, you have basically it has to predict two things, but in a multi-class classification, I have to predict many different possible classes. It's a harder problem. So in the binary, I have only two classes, and I will just predict two classes. There's also the notion of the object here, does it have only one label or many labels? So this is what we call a single label classification. So every single one of them here, when I'm predicting their labels, there's only one label. But there's some problems where every single one of them may have more than just one label. For example, I don't know, I have an image and I say, what are the animals in there? It's not that there's a dog or a cat. Maybe there's a dog and a cat and a giraffe and an elephant. There are more things inside, not just two or one. Or for example, I have a document and I say, predict the topics that are discussed there. Well, the document may talk about more than just one topic, but many topics, the same document. So that's what we call multi-label classification. There's another issue that is important in machine learning, and that's extremely important in precision health, is the concept of explainability. So I mentioned that you have some training data, and we build a predictive model. Many techniques, actually, the predictive model is a black box. A black box, it means that when I'm using it to predict something, for example, does it have cancer or it doesn't have cancer, when it predicts it, even though the accuracy is high, when I ask it, why is it that it's this class or that class, it's not able to explain it to me. And that's why we call it the black box, as opposed to techniques where when I learn the predictive model is transparent. I can see the rules inside and I can interpret them. So there's a notion of interpretability, there's the notion of explainability. Interpretability, it means that when I learn the predictive model, I can see what has been learned and I can interpret the predictive model. The explainability is after I do a prediction, I ask it, why did you predict that class rather than that class? It is able to explain it to me. So the black boxes, it means it's not interpretable and it's not explainable. Transparent model, it means it's interpretable, still not necessarily explainable. Okay. The advantage of an interpretable model is not only you can see what's inside, but you can change it. Because maybe there's knowledge that the application domain expert has that on knowledge that is not reflected within the training data. So the predictive model has never the chance to learn it because it's not in the training data. So I can add it to the model. There's another notion that is also very important in precision health, is the notion of balanced and imbalanced data. So often the techniques that have been proposed assume that the data is balanced. So when I'm giving it training data, I give it as many observations from this class as I'm giving it observations from the other class. So it's balanced in that sense. But in many cases, in most cases actually, you go to, for example, where we do screening for breast cancer, well, the majority don't have a breast cancer. The majority are fine. It's a minority that have a breast cancer. And same thing, if you go to the office of an oncologist, the majority who are referred to the oncologist have actually breast cancer. It's a minority that where false positives are sent there. So you always have an imbalanced data set. Okay, so imbalanced data set, to train with an imbalanced data set, it's very, very hard. It's way more difficult because the majority class will overwhelm the minority class, and the minority class is not well expressed, so that you can't find patterns to have them in the predictive model. So the predictive model is biased towards the majority class. Okay. What did I want to say here? So what basically you have to keep in mind is that there are two phases. One phase is the learning, so I'm giving it an input data. The learning happens and I learn a predictive model. And then there's another phase. Once I'm happy with the predictive model, I have the predictive model and some evidence, and then I do the prediction to what is the prediction is to label the this evidence with some class. Now, how do what are the techniques that exist? There are many techniques. They all use the same kind of framework in terms of supervised learning. You have data that has been labeled. Okay, here, I'm trying to use my mouse to show you. Have labeled data. That's what we use for training. Actually, not really. We will split it in two parts. One part that I will use for training, and one part that I leave on the side for later for testing. So the training is used to derive a classification model, so classifier. And then when I have a classifier, I will test it on the testing data. And only when I reach an accuracy that is acceptable on the test data, so the test data was not used for the training, okay, only when I reach an accuracy that is acceptable, then I can deploy it, and I use unlabeled data to label them automatically for me. Okay? So many techniques use the same kind of framework. We have k-nearest neighbors, decision trees, neural networks, Bayesian classifiers, associative classifiers, case-based reasoning, genetic algorithms, rough set theory, and so forth. I will just focus on the three top ones. But before that, I'll do a small pause to see if there are any questions. Any questions from the audience? No? Okay, you're still there, I hope.
Yes, they are still there.
Okay. So let's start with, so I chose these three on purpose because they're very simple, but they're completely different. They're completely different, yet they do the same thing. Remember these things. So I will give them data. They will learn some model. That model will be used to label data at, this is what we call the inference. This is the learning on top. This is the learning, and this is the inference. So they all have the same thing. I give them some training data, they learn something, and then I'll use what I learned to label something that hasn't been seen before. And okay, I'll go back here. So those three are completely different. Let's start with the k-nearest neighbors. K-nearest neighbors is a very, very simple technique that is actually not learning anything. we call it lazy learning. Lazy learning basically uses an example from the training data that is as close as possible to what I'm trying to label, and then it checks the label of the training data that is similar to it, and it uses that. So it classifies by analogy, let's say. It needs some measure of similarity. So here's visually what happens. I have my training data. Okay? In this case, I have only 2 classes. And these 2 classes, I'm not learning anything. So there's no learning. I'm not building any model, nothing. At one point, I have a new entry that I haven't seen before, and it's not labeled. That's why I don't have a color. So what I do, I need to color this. Okay? And to define the color of this new object, I will just look in my data, supposedly training data, but I'm not training. I'm looking at the data here that I have labeled already. I look at which one is the closest. So I need this distance function to measure similarity. And the closest one, let's suppose, is this one. Oh, it's blue. Then this new entry must be blue as well. Okay. So this is what we call the nearest neighbor. And there is another notion called the k-nearest neighbors. So k-nearest neighbors is like the nearest neighbor, but instead of using one similar object, I will use many. So the k-nearest neighbors. So here's my object that I need to label. Again, I'm not training, I'm not learning anything. I just leave them aside. And then when I get this new entry that hasn't been labeled, I look at the k closest, most similar records in my data. And then, oh, I have all these. Okay, suppose it's 5, the 5 closest. Oh, I have 3 red and 2 blue. Well, they will vote. I have more red than blue, then this must be red. That's it. You see, it's very, very, very simple. I may have another version that is weighted. So here they voted 1, 1, 1, but I may use the distance between these guys and this object that I need to do and use that distance as a weight of some sort. So I can have a weighted k-nearest neighbor as well. There are different variations, but in general, that's what the method is doing. You all understand that? Simple. Okay. And this is called lazy learning. I didn't learn anything. Okay? And that means that I have to keep in memory available the whole data, because I'm not creating that cloud that I showed before, which is the predictive model. There's no predictive model. I'm just calculating the k records that are the closest to the one that I need to label, and I make them vote and I label that. Very dumb, but it works. In many cases, actually, it's very, very, very effective. But here's another method. Was very popular, still popular actually today, called decision trees. And to illustrate this, I'll give you an example. This is an example that I took from the paper that introduced this idea in the 80s, so a long time ago. The first algorithm was called ID3, presented by Quinlan. And in his paper, he had this example when he plays tennis and when he doesn't play tennis. So this is what you see in this table. And you have descriptions of the weather. What's the outlook? What's the temperature? What's the humidity? Whether it's windy or not. And here, this is the class label. I'm playing tennis or I'm not playing tennis. So N means I'm not playing, P I'm playing. And these are the observations in the past. And I want to build a classifier that will predict automatically, given the conditions of today, predict whether I will play or not. Okay? So that's the classification that I'm going to do. So basically, and on purpose, I colored the not playing in orange and playing in gray so that you can see the different cases. I could build a tree like this. What's this tree? Well, this tree here, I have nodes that are blue, and I have nodes that are yellow, and I have nodes that have the class label. These are the leaf nodes. So in the beginning, when I start here, I ask a question. The blue means I'm asking a question about one particular feature, or we call it attribute or field. So what is the outlook? And in yellow here, I have the 3 different possibilities. And you can see outlook can be sunny, it can be overcast, it can be rain. Well, I basically, it's like having all the data in this first node, and then I'm dividing them, all the cases that are sunny here, all the cases that are overcast here, and all the cases that are rain on this side. And you notice that every single case that has overcast is actually play. Overcast, 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 overcast. You never have overcast in orange. So I immediately can say that if the outlook is overcast, I'm going to play anyways, regardless. However, if it's sunny, if the outlook is sunny, I have sunny in red. Oh, but I have sunny also in gray. So I don't know. I may play or I may not play. Then I ask another question, humidity. So I ask another question on another attribute. So is the humidity high or the humidity normal? And based on these 2 values, I will determine, based on this data, whether I will play tennis or don't play tennis. And this is basically how I can interpret this what we call decision trees. It's a tree of decisions. The decisions are in these leaf nodes. And what I learned is this tree. By going through this data, I build this tree, and this tree represents the prediction model. Then when I have to predict something, I look at, what's the overcast? Is the overcast rain? Okay. Then if it's rain, I'll check if it's windy. If it's windy, true, then I will not play. Okay, that's how I will make my prediction. So the prediction is explainable, it is interpretable. But the question is, how do I build this? Okay, this is not the only tree that I can have. There are many possible trees. Okay, so how do I build this tree? And the algorithm that I will use to build this unique tree is the learning, basically. And then there is an algorithm which is recursive algorithm. It means it calls itself again and again. So in the beginning, I have all my data in one node. Okay, this tree starts with a single node representing all the data. And then I go through this data and I said, in that node, and I say, do they have all the same label? If they don't have the same label, then I have to split them. And I split them how? I will select one particular attribute, one of these fields, that best separates these 2 in individual class, 2 or 3 or 4, depending on the classes that I have. But here's typically for 2 classes, so it's a binary classification. And once I do that, I will ask myself again the same question. Each of these nodes, all the data, do they have the same class? If they have the same class, then I label it, I'm done. I have a leaf node. Otherwise, I have to select another attribute and split it again. And keep on doing it recursive. Okay. And when do I stop? When I don't have any attribute left, I use all the attributes, then the node will become a leaf node with the label of the majority of those records. I stop also when I split it, but there's no record that has this value, it's empty. Or I don't have any, I stop when all of them belong to the same class. So the question that remains is, how do I select an attribute each time? And well, there are techniques to select the best attribute, and the best attribute is based on some information, based on information theory, calculating the information gain that I get for each of those attributes, and I take the one that gives me the best information. So basically, I build this tree, and once I build the tree, I use it for inference. It's way better than the k-nearest neighbors. However, this technique is known to what we call overfit. So that means it can become very good for this data and data from the same distribution. But as soon as I have data that is not from the same distribution, then the performance goes down. It's not very good. Okay, so that's two methods. What do I have? I have training data, and my goal is to be able to, given some data that hasn't been labeled, to label it automatically, predict for it. And here's another method, a method based on neural networks, artificial neural networks. And the people who created this idea in the 50s, so it's not new, they were inspired by how the neurons work in our brain. Inspired. We're not mimicking them at all whatsoever. It's completely different. We actually don't even know how exactly they work in the brain. In the brain, we have different types of neurons. They're not all the same. We have different classes. We have around between 90 billion and 100 billion neurons in the brain. We have other neurons too, not just in the brain, by the way. Each one of them has about 10,000 connections. So it's phenomenal compared to what even the large networks that we have today. They're not comparable to the brain yet, especially the number of connections. So if I zoom in and look at only one neural network, one neuron, we call it a perceptron. One neuron, what do we have? We have basically many connections coming, each one, n connections here, n connections. Each one of them has a weight. And this weight here represents the strength of the connection. So this is like the dendrites in a neuron. They're not all the same kind of strength. They have different strengths. So here I'm representing them by weights. And some of them may be negative because you have some connections that are inhibiting actually the action. Some are exciting, some are inhibiting. So you have positive and negative weights. And they come to this, we call it transfer function. They are summed up. Okay, we call it the soma, actually, in biology. And then there's a bias that is added to it. And here an activation function that decides, oh, what do I do with this? Should I actually continue the message along the axon to the next level, actually, to whoever is listening to me, or not? Okay, and there are different kinds of activation functions. So you put them together in layers between what we call the input layer and the output layer. You have many layers here, and you have connections between one layer and another layer. And on all these connections, you have these weights. Initially, the weights are random. The goal is to learn what are the appropriate weights I need to label. And the output layer, I express the class labels. I want the propagation of the message from the input to the output. So let the information propagates to the output layer. I look at the output layer. Do I get actually what is the label that I have in the training data? If it's not, then I made an error, and I correct the error, and I back propagate it and adjust the weights. And I keep on doing this for next one, and I have many epochs going like that until these weights converge to a value that will allow me to predict the right label. The information goes feed forward, and then the error will go backwards. That's what we call back propagation. I think I do it here. Yeah, this is the training data. So I take the data here and I represent it in blue. I hide the label. I take only these features. I'll pass them in here. And then when it comes on the outside, I will compare what I get here with this label that I have here. And if it's not correct, then I change these values layer by layer and I repeat that and repeat that until they converge to something that I'm getting here, which is a matrix of all these connections. It's equivalent to the dendrites, and the activation function that sends the message A is like when the cell decides to send the message along the axon. That's as close as we can get to the reality, but we don't know how the brain functions actually. Now, this technology, neural network, existed, as I said, since the 50s, but it changed quite a bit recently because the computers allow us to have way more sophisticated networks. So in the past, what we had to do, we had to engineer the input layer so that we can feed the engineered features that we extracted from the image. So imagine this is the image. I extract features, I engineer them. For example, the average pixels here or whatever. This is something I did myself for mammography detection. And then these features are propagated. So the information that I have in these cells, these neural nodes, are propagated till the end here. In deep learning, not only I can have more layers, but I don't have to engineer features. I actually can feed the whole image, and the neural network will decide what are the features that are relevant. I don't have to engineer them. It's more powerful, but also it generates a network that is even more difficult to explain and more difficult to interpret. So that's why it's a black box. But the advantage of these artificial neural networks is that their accuracy is phenomenal. It's very good. And they're robust to noise and things like that. However, they take a long time to train because of all these repetitions until they converge. As I said, they're very difficult to interpret. If you have extra knowledge that is not expressed in the training data, you cannot inject it manually, because when you change, what's the knowledge here? These are weights. If you change the weight of one of the connections manually, you have no idea about the repercussion on the whole network. So nobody does. Yeah, unhidden, predict its label. Okay, that's the idea. So in all those cases, whether it's the decision tree, the neural network, or k-nearest neighbors, I have data that is for training, and I learn something, and that something is used. It can be a set of rules. It can be a decision tree, like I showed you. It can be formulae. It can be hyperplane crossing the hyperspace, like can support vector machines, or it can be neural network. Okay, it doesn't really matter. Basically, I will use what I learned to automatically label instances that I haven't seen before. Okay, I think I'm going to stop here. See how much time. Okay, we have some time for discussions. You didn't ask me questions in the middle, so I hope you have questions now.
Yeah, so yeah, thanks for the great lecture. I know you touched on supervised learning quite a bit, so I was just kind of curious where like reinforcement learning comes into play in artificial intelligence, because it seems like a lot of these big projects by DeepMind and such utilize reinforcement learning, and in reinforcement learning or in supervised learning, you kind of talked about kind of the need for a lot of data for your training sets, but in reinforcement learning, you can make use of Markov decision processes, and you don't really need that training data. And it just seems like, yeah, wouldn't it just be easier if you would just use reinforcement learning for everything? But obviously it's not that simple. So can you kind of just touch on the differences and why you would choose one over the other?
There's a huge difference. There are two complete different philosophies on how to learn. So in supervised learning, I have supervision, and supervision is data that has been labeled. And I typically have to have a lot of it. For example, I have many pictures of dogs and cats, and I have to say, these are the cats and these are the dogs. And then the system will go through this, like I showed you, to finally build something that converges, and then I use that to detect what is a dog, what is a cat. Now, and I chose three on purpose. One that is lazy learning, one that generates a decision tree that I can interpret what makes it a cat and what makes it a dog. And finally, I use the neural network because it's completely opaque. I don't know what it means, this weight and this bias and this. It's just a network, and I can use it as is, and it's very good at telling me what is a cat, what is a dog. But there are many other methods. Now, reinforcement learning is not for those kinds of problems. Reinforcement learning, it's used to learn by trials and making mistakes and making things right until I learn to make more things right than mistakes. So, for example, you ask a dog to roll. The dog doesn't know roll. But sometimes by accident it rolls when you ask it to roll. And it notices that when it did that, you gave it a treat. Whether you were happy and you petted it or you gave it something to eat. And then maybe it forgets about it. And then when you say roll, it may not roll. And then by accident, it rolls. And it notices that each time this master says roll, and I roll, I get a treat. So it's based on what we call a reward. Okay? And a robot is the same. So in the case of a robot, you can teach it to do something, also with reinforcement learning. It has different actions that it can do. Sometimes the number of actions is very big. Okay? The dog can roll and can do other things. So the robot has many actions, and it will choose one action, and the program knows that that's the goal. I want you to go and grab this. Sorry, you cannot see it, but let's say, go and grab my glasses. Okay? And if I don't grab the glass and I take another action, then I'm not getting a reward. The reward is a number that I have to maximize, number +1. As soon as I touch it and I grab it, now I give you a reward. So the program is to learn a policy. What are the actions to take given the state I'm in? And the state can be, oh, I told you to grab the glasses, or I told the dog to roll. So it's like a child learning. A child also, same thing. Doesn't know the language, is learning about the space it's in, but it starts finding relationships between the reward it gets, getting a sweet or getting a punishment, don't do that, and the actions it took. So again, reinforcement learning is learning a policy that tells you what action to take to maximize a reward down the road, given the state I'm in. Okay. And both can work together. Sorry, both can work together.
Yeah.
Example, I may learn from data that I have in the past, what is the action I should take? So I can build a supervised learning method to decide about, so the actions that I could take could be the buckets that I talked about. And I can learn from, if I have the luxury to have data from the past, I can learn to take an action. Then I take an action and then I check my reward. If my reward is positive or negative, then I want to maximize it. I will choose something else. I can give it back to the system that is learning. So I learn at two different levels. Now a system like let's say AlphaGo. Okay. AlphaGo is also using reinforcement learning because any action it does on the board, the state is the board, and then the action is moving this or moving that. There are many things that I can do. When I take an action, I can evaluate, am I winning or am I losing? And the evaluation is complicated depending upon the game. Do I do it one step forward or deeper or things like that? But I have something to measure that tells me I'm winning or I'm losing, or I'm improving my state, my position or not. And that constitutes the reward, basically. And if I play against myself again and again and again and again, I end up learning. what are the best actions to take given a situation that I have in front of me at this state. Am I addressing your question?
Yeah. I'm also a bit curious. You said, like, given a classification problem, like let's say you're given an image of a dog or a cat, reinforcement learning wouldn't be too suitable for a situation like that. But can you not model that classification problem in a way where you can use reinforcement learning? Kind of like if you're trying to teach a kid how to classify between two different animals, right? It'll randomly say it's a cat, and then if it's not a cat, you don't give them candy or whatever. But if they choose the dog and it is a dog, you give them a reward. So
again, it takes longer. So if
okay.
if you have data, so it depends upon the situation. If you have the luxury to have data that is labeled, might as well use supervised learning. In reinforcement learning, you don't have that luxury. You don't have data that you have to learn from. You learn from experience, from trial and error. That's where you learn from. So if you have some data, often you have some data that you received from the past, then you can use it to build on top some supervised learning to help you choose the action rather than having it random. Rather than having it random, I select a subset. Then I increase my chance to converge faster. Because otherwise, if I'm waiting for serendipity to help me, it can take a long time.
Yeah, got it. Makes sense. Thanks.
So, any other question?
Other questions?
Ram, you're sitting at an emergency exit. No, it's okay. I'm just teasing you. I don't know the situation.
Yeah, sorry, I'm not sure if you can hear me okay. I was just wondering, would you be able to talk a bit about your research work? I found your LabWeb page, but I couldn't really understand. I'm not that familiar with computer science, so I was wondering if you could explain it.
Oh, I work on many different things. I don't know where to start. So I have, for example, work on detecting diabetic retinopathy, and I talked about it last time. So that's pure supervised learning. I also try to identify biomarkers for people who have some particular diseases, like in mental health. I have work that is related to detecting faults in machines. So imagine a machine that fails. If you don't stop it, it can get worse. So imagine a conveyor belt. Conveyor belt is a machine, or an elevator, or whatever, escalator. You often see them out of order. So can I predict when it'll fail? So often people, for these machines, because they don't want them to fail, they do maintenance, regular maintenance. But maintenance is expensive because you have to send people, you have to add oil here, change this part there, and whatever, even though it's not failing. But by intervening and making that maintenance, actually you can make it fail. So when to do the maintenance is complicated. It's better to, instead of schedule regularly the maintenance, you can actually predict when is the best time to do the maintenance based on some data that you get from the sensors. What if you can't go and maintain it and you know it's going to fail, or you know it failed? Can you make the machine adapt to the failure and continue to work? So suppose you hit your elbow somewhere and it's hurting, okay? But you need to grab that glass of water and you can't extend your arm completely. Instinctively, you'll adapt. You extend partially and then you move your body to grab the glass of water. You adapt it. Can a machine adapt as well? Why is it important? Well, suppose I have a machine that I can't access to maintain. For example, the machine is in Mars or in space somewhere. The next time I will go and fix it is when I send astronauts again there. It'll take forever. So can I have a machine that can adapt to the new situation? It's broken, or it's not 100%. I can't extend my arm fully. I can extend it partially. But I still need to do, I still need to continue my mission on the moon or on Mars or whatever. I'm saying the case of space because it's obvious, but it's
on one machine at a time. So how would that, like, why is that an issue, right? Because there's so many large language model providers that lets you use a large language model as an API. Everything's in the cloud nowadays, right?
yeah, but still, when they are very large, they are working on
Mhm.
very large infrastructures that cost a lot of money, and they're very expensive to run, to maintain, to cool down. You have no idea how much it costs to cool down these machines. And it's not one person,
Yeah.
you're not the only one. You have a million people at the same time. So it would be nice to have it on your phone. But to have it on your phone, you have to have it in a reasonable size.
Right. Okay. Yeah. I mean, I guess that goes to like just a larger problem in general where infrastructure for cloud is just becoming so.
But imagine you have now a robot with a language model. Imagine you have a smart speaker that has a language model in there. You're not going to use it just for, hey, play this music or what's the weather now in Edmonton. You will use it to chat, reality, in real stuff like a person. In that case, you can't afford to have it just on the cloud for 1 million people at the same time. Ideally, you have to have it localized.
Right. Yeah, that makes a lot of sense. Yep.
Okay. I have to run to another meeting.
Okay.
I'm late. But thank you, guys.
Yep. Thank you.
I hope it was useful.
Thank you so much.
Okay. Take care.
Bye, guys.
Bye.